Hello everyone. So in this lecture, I'm going to give you some insights into the implementation aspects of IS 15462, the 2019, the recent code that was released with regard to the use of modified bitumen. In one of my previous lectures, I had talked to you regarding the parameters that are focused in this IS 15462. I did not get into the details, and that was again 1.5 to 2 years back. So, but in these 2 years, there are a lot of issues with regard to the use and the implementation of this particular code. So, in this lecture, I thought I'll focus on some of those aspects. Basically, this is the outline of this talk today. We are going to discuss the salient features of IS 15462. I'm going to show you the older code and the new code and make some comparisons between the two. Then we are going to look at some of the modified binder specifications across the world. So here I have chosen to focus on European Union, the South African specifications, and the US specifications. After this, we will look into the MSCR, which is an additional test which is required for polymer modified bitumen and its implementation in USA. Basically, the PG framework was implemented in USA, and after a period of time, it was understood that it was more applicable for unmodified bitumen, and it had some issues when it comes to polymer modified bitumen. In fact, there is one study, I think it was published in 2012, wherein they had used different kind of binders, an unmodified binder, two types of elastomer modified binders, some plastomer modified binders, etc., in an accelerated loading facility. Again, some grades were kept constant across the binders. And they had observed that the performance of the unmodified binder and modified binder were totally different, though they are classified under the same grade. We can have these kind of an issues in a viscosity grading or a penetration grading system, but the main aspect of performance grading itself is to identify binders which will have identical performance. So then if it is not exhibiting identical performance, then there is some issue that needs to be focused. So that is when people suggested that we should have some additional tests, say for example, a PG plus test. Right. So an additional test which is specifically applicable for modified bitumen. So many tests have been proposed, and one test which is gaining importance is this MSCR, multiple stress creep and recovery. So we are going to focus on this test and its implementation in USA. Then we'll focus on some issues in implementing the IS 15462 2019 version. And then finally, we would summarize. Right. So to first begin with, this is the IS 15460, the older code, 2004 version. So therein we had only one code for all types of modified bitumen. We basically had 4 tables. The table 1 is for plastomer modified bitumen. You can see plastomeric thermoplastic based type A. The second table is for elastomeric thermoplastics based type B. Table 3 and 4 are for crumb rubber and natural rubber modified bitumen. But then when the newer code came, the 2019 version came, it was split into 2, right? The IS 15462 code focused only on polymer modified bitumen, both elastomer and plastomer modified bitumen, and the natural and crumb rubber modified bitumen were addressed in a separate code. It is IS 17079. I had discussed about it in my previous lecture as well. So here for today's discussion, we are only going to consider the elastomer and plastomeric modified bitumen. So we are going to deal with the 15462 table 1 and table 2 and the newer 15462 2019 code. Right. So now let us start with the older one, which is we'll just discuss the parameters that are measured using this code. If you look at it, you can see penetration at 25 degrees Celsius is the first parameter that is measured. Then we have softening point, frost breaking point, flash point. Then you can see it is a plastomer modified bitumen. So the 5th parameter is either elastic recovery at 15 degrees Celsius or the G star by sine delta. Okay, so if it is G star by sine delta at this specified temperature, the value has to be a minimum of 1 kilopascal. Then we have separation, viscosity at 150 degrees. And then we also have tests on thin film oven residue. right? So this is with regard to the plastomer modified bitumen. But when you look into the elastomeric modified bitumen, all of them or most of them remain the same. At least the parameters remain the same, except for this elastic recovery. Previously, it was specified that we could have either elastic recovery or complex modulus. But in the case of plastomer modified bitumen, only elastic recovery is specified. The complex modulus value is not specified. Right, I'll touch upon this in a while. If you look at the elastomer based bitumen, only elastic recovery is specified, whereas for the plastomer based bitumen, either elastic recovery or complex modulus is specified. Now you should understand why this kind of a variation is given between these two type of modifiers. To understand this, you should link it with the interaction mechanisms that we had discussed for modified bitumen. So for an elastomer modified bitumen, we had discussed that the SBS kind of modifier, we have a styrene, polybutadiene. So this polybutadiene is soft and rubbery. So it gives this elasticity. So one comes from the modifier. The other one comes from the interaction mechanism. In the case of elastomer modified bitumen, we said there is a three-dimensional network formation, and this network formation is able to give this elastic recovery properties, right? So that is why the elastic recovery property of an elastomer modified bitumen is generally said to be better when you compare it with the plastomer modified bitumen. For a plastomer modified bitumen, the interaction is only based on chemical crosslinks. Right, so these chemical crosslinks are going to remain as hard and stiff points, and this advantage of this network formation is not present in this plastomer modified bitumen. So that is why option is given to measure either elastic recovery or complex modulus here, whereas elastic recovery is a mandatory parameter for elastomer modified bitumen. Right. Now, when we come to the new code, which is IS 15462 2019, grades are specified. We basically have 5 grades: PMB 64 minus 10, 70 minus 10, 76 minus 10, 82 minus 10, and 76 minus 22. And they have given when each grade is applicable. Say, for example, if you take 64 minus 10, it is applicable for locations having an average maximum pavement temperature, which is less than 64 degrees Celsius, and minimum pavement temperature greater than minus 10 degrees Celsius. So from the lectures on performance grading, you all should know how to calculate the 7-day average maximum pavement temperature. Right. So based on that, we have 5 grades which are specified for India. Again, there is no demarcation here whether it comes from an elastomer modified bitumen or from a plastomer modified bitumen. Basically, we have to meet these grades, and you don't have to worry whether it is from an elastomer base or a plastomer base, as long as it meets the required specifications. Now let's have a look at the code. Right, so this is the specification that is mentioned for these 5 grades. Let's start by looking at the test parameters that are specified for the original binder, which is the unaged binder. So we have the softening point as usual, elastic recovery at 15 degrees. So you can see here, whether it is an elastomer or a plastomer based bitumen, you have to meet this elastic recovery requirement. Then flash point, viscosity at 150. Then we have this complex modulus, which is G star by sine delta. As we know, it has to be a minimum of 1 kilopascal, and it should have a minimum of 1 kilopascal value at this particular test temperature. This test temperature is nothing but the at grade temperature. Say, for example, I have 64 minus 10. The G star by sine delta value should be a minimum of 1 kilopascal at 64 degrees. If I take a 76 minus 10, it should have a minimum of 1 kilopascal value at 76 degrees. As you're aware of, this G star by sine delta value will keep decreasing as temperature increases. Right? So depending on the specific grade, it has to be tested at that particular temperature. The other additional parameter which is given here is the phase angle. The phase angle basically gives you an idea of the extent of elastic and viscous components that are present in this material. We know that the phase angle is 0 for a purely elastic material, and it is 90 degrees for a purely viscous material. So depending on the phase angle value, we can know whether it is tending towards a more elastic kind of a response or towards a viscous kind of a response. So for all the grades of bitumen, the phase angle is limited to a maximum of 75 degrees. Then we also have separation, which is the difference in softening point and frost breaking point, as which is present in the previous version. Now let us look at the tests which are supposed to be carried out on the rolling thin film oven residue, which is nothing but the RTFO residue. So we have loss in mass, again the complex modulus. So here the specification is minimum of 2.2 kilopascal, because we age the material, it kind of generally tends to stiffen. I will just put it generally. It has to be a minimum of 2.2 kilopascal. So again, you test at the at-grade temperatures and you determine the specific, whether it is meeting the particular grade. Then we are also required to carry out this MSCR test, which is nothing but the multiple stress creep and recovery test. Now, similar to the MSCR test specifications given by AASHTO M332, here also we have 4 traffic conditions: a standard traffic, a heavy traffic, a very heavy traffic, and an extremely heavy traffic. So in a while, I'll tell you what these correspond to. So for each of this traffic level, the JNR value and JNR difference is specified here. So we know that we carry out this MSCR test at 2 different stress levels, 0.1 kilopascals and 3.2 kilopascals, right? And we calculate the JNR value. You know how to calculate. I've already explained it before. So this specification parameter here is JNR 3.2, because we want to evaluate how this material responds to a higher stress level. So that is why for the case of specification purposes, we are taking 3.2 kilopascal. So for a standard traffic, if you want to use a binder for a standard traffic, this has to be a maximum of 4.5 kilopascal inverse at 64 degrees Celsius for a PMB 64-10 grade of binder. Similarly, the JNR difference, basically it's stress sensitivity. Like when you increase the stress level from 0.1 to 3.2, how is the deformation varying? Whether it is suddenly showing higher strain values at a higher stress level, or it is kind of susceptible to the increase in stress level, right? So that we understand by this JNR difference parameter. So this is specified to be a maximum of 75%. The difference has to be a maximum of 75%. So this is for a standard traffic. Now I can use the same PMB 64-10 binder also for a heavy traffic condition, right? Because this grade here, PMB 64-10, comes from the temperature, climatic conditions of the location, right? So depending on the climatic conditions of the location, I will decide whether I need a 64-10 or a 70-10 or a 76-10 or an 82-10 and so on, right? So this grade comes from the climatic conditions. This particular letters here, S, H or V or E, addresses the traffic condition. So now if I have a particular binder, let's say PMB 64-10 binder, which I have to use it for a heavy traffic condition, in that case, I do an MSCR test. I determine what are the JNR 3.2 and JNR difference values. So this JNR 3.2 should be a maximum of 2 only. So you can see here we have allowed it to go up to 4.5, whereas here we limit it to 2. Basically, this JNR value kind of tells you what is the proportion of the unrecovered strain. So at a higher stress levels, we want to minimize this value. Similarly, this JNR difference is limited to again 75% for all the cases. The only difference is the JNR at 3.2. So for a very heavy, it is limited to 1. And for extremely heavy, it is limited to 0.5. All right, so this is with regard to the MSCR test. This is usually carried out on an unaged binder, right? So we have grades designated as PMB 64-10, S or H or V or E, depending on the traffic requirement. Now let's look at the tests which are carried out on a pressure aging vessel, which is nothing but a PAV residue. There is only one test which is specified here, which is complex modulus, G star times sine delta, and it is limited to a maximum of 6,000 kilopascals, and it has to be carried out at the specified temperatures. Right? You can note down the temperature range here. it varies from 31 to 40 degrees. Just remember the temperature range. I will discuss the details related to it a few slides later. Right, so this is the code in brief. Now let us look at the applicability of the binder grades for different conditions. So I told you we have a standard traffic, a heavy, a very heavy, and an extremely heavy. So what is the standard traffic condition? Which has traffic, the repetitions less than 10 MSA and traffic speed which is more than 70 km per hour. So you should be aware of the influence of loading time on the material response. Bitumen being a viscoelastic material, if we have higher loading times, its modulus value is going to reduce. So we have seen this earlier as well. So that is why for a standard condition, the speed is specified to be greater than 70 km per hour. So a higher speed, we have a lower loading time. Then we move on to the heavy service condition. The traffic levels here are between 10 to 30 MSA, or you can have a slow moving traffic. What do we mean as a slow moving traffic? Between 20 to 70 kilometers per hour. Then we have a very heavy service condition wherein we have traffic levels greater than 30 MSA or very slow moving traffic, which is less than 20 kilometers per hour. An extremely heavy condition is defined as traffic which is greater than 30 MSA and very slow or standing traffic, right, which is less than 20 kilometers per hour. These are the traffic levels. Now, depending on the pavement temperature range and the traffic condition, we can identify binders. So this will be designated. Let's say, for example, I have a traffic condition which corresponds to heavy and pavement temperature conditions which correspond to 64 and minus 10. I would require a PMB 64 minus 10 H binder. That H you have to add it here. Right? Say, for example, let me write it. We will have a H binder here. Okay, so which means that this binder will give the desired performance. Again, what is this desired performance? You have learned it from the PG lectures. So this binder is going to give you the desired performance for a climatic range of 64 to minus 10 and a traffic condition which corresponds to this heavy. Okay, so this is how we grade binders using the IS 15462 2019 specification. Right, now we will look at some of the other codal provisions available across the world. Now let's look at the European Union specifications for modified bitumen. I have not shown you the code, but I have just summarized the parameters that are specified in this code. They essentially give you two tables. One is the additional requirement, one is the essential requirement, and the other one is the additional requirement. So what are the parameters specified under unaged condition as essential requirement? Penetration at 25, softening point. They also have something called as a force ductility test or a tensile test. So what is this force ductility test? It basically calculates the deformation energy that is involved in taking the elongation of a sample from 200 mm to 400 mm. Basically, it's like a ductility test. You do it under controlled conditions until you reach a deformation of 400 mm. Then we calculate the deformation energy required when from the elongation of 200 mm to 400 mm. So that is quantified in this particular test. Then we also have a flash point. When you move on to the short-term aged condition, we have change in mass, retained penetration, increase in softening point. They do not specify any test on long-term aged condition. Similarly, if you look at the EN specifications, for additional requirement, we have frost breaking point. Here you can see we have elastic recovery at 25 degrees Celsius, 10 degrees Celsius, the plasticity range, and the storage stability, or which is nothing but the difference in penetration. You can see we do not have any PG or we do not have any MSCR here, which is specified by the European Union. Right. Now let us look at another specification, which is from South Africa. South Africa essentially has different tables again for different type of modified bitumen. One table for polymer modified bitumen, one table for rubber modified bitumen, another table for hydrocarbon modified bitumen, and so on. So what are the tests and parameters measured from for this particular specification? In the unaged condition, we have softening point, elastic recovery, This is for a polymer modified bitumen, right? So we have elastic recovery at 15 degrees Celsius. We have dynamic viscosity. You have to note the temperature, 165 degrees Celsius, storage stability at 185, flash point. In the short-term aged condition, we have a change in mass, softening point, and elastic recovery at 15 degrees. If you look at rubber modified bitumen, there are different tests that are specified. We have the conventional softening point. The dynamic viscosity, sometimes it is mentioned as 170 or 190 degrees Celsius. You can see the increase in temperature here, right? Then we have compression, a specific test, compression recovery, which is specified for the rubber modified bitumen in specific. Another test, resilience, which is again mentioned for rubber modified bitumen. Again, I will not get into these tests because it is not very relevant to what we are trying to discuss here. Then there is also flow test at 60 degrees here. Now, if you look at for the hydrocarbon modified, softening point, penetration, dynamic viscosity at 165, storage stability at 180, flash point. For rubber, you don't do any test on short-term age or long-term age condition. For hydrocarbon, we have the similar mass change, softening point, and then we have retained penetration here. Right. So I also have the specification. This is for the elastomer modified bitumen. We have two types, E1 and E2, and one plastomer. I'm sorry, this is for the polymer modified bitumen. Right. So we have E1, E2, and a plastomer. So you can see these values will vary depending on the type of modifier, but these are the parameters that are mentioned. Similarly, if you look at the rubber modified bitumen, you can see here that we have AR1, SR1, AR2, and SR2, 4 different kind of binders. And you can see here the dynamic viscosity is mentioned at different temperatures depending on the type of binder. Now let's look at closely at the specifications which is given by USA, because we follow the current version of IS 15462 2019 follows more closely with the specifications that is available in the USA. Right. So this table, I think you're familiar with. We have different grades: 7-day average maximum, 1-day minimum pavement temperature. Then we have the flash point, viscosity, dynamic shear. So all these are an unaged binder. Then we have the RTFO. So this is the same PG table. And you can also see here, this is with the MSCR test, right? This is from ASHTO M332, which incorporates the MSCR test also into the specification. So here we have tests on rolling thin film oven residue. We have the MSCR test. It is kind of similar values. 4.5, 75%, 2, 75, 1, 75, and 0.5 and 75. Okay, the test temperature also is given here is the at grade temperature, which is corresponding to the specific PG grade. Then we also have the PAV temperatures. You can see, but what they have done is the G star times sine delta value is specified differently for different traffic conditions. For the standard traffic condition, it is sufficient if you limit it to a maximum of 5,000 kilopascal inverse. 5,000 kilopascal. Whereas for heavy, very heavy, and extremely heavy, it has to be limited to a maximum of 6,000 kilopascals. Right? But in our code, we do not have these kind of variations depending on traffic. Now let us look at the implementation of MSCR in USA. I'll just tell you what these codes are to understand the subsequent figure. We have 3 codes. ASHTO M320 is our original PG specification. Now ASHTO M323 is the original PG specification with grade bumping options. You would have learned about what grade bumping is. Basically, to cater for these higher traffic conditions, we increase the grade of the binder. We bump, like say, for example, depending on the climatic condition, if we get a PG64 binder, then depending on the traffic condition, it might become a PG70 or a PG76 binder that is required for that particular location. Okay, so this is generally done for unmodified binders when you do not have this MSCR test. Okay, so that is addressed through ASHTO M323 specification. Then we also have ASHTO M332 specification, which incorporates this MSCR, like which I showed you now, right? So this is from ASHTO M332 specification. So basically there are 3 codes with regard to the performance grading system in USA. The original ASHTO M320, which is for unmodified bitumen, or which was originally introduced. ASHTO M323, which incorporates grade bumping. ASHTO M332, which uses the MSCR test. You should remember that when we have the MSCR test, there is no grade bumping, because those letters S, H and all those things from the JNR value takes care of the traffic conditions. But we did not have that kind of a provision in the earlier original PG specification. That is why it was introduced separately in ASHTO M323 specification, right? And there are many other PG plus tests. MSCR is actually one of the PG plus tests, but we have many other PG plus tests also, right? Now let us look at the implementation of MSCR in USA. So we basically have like 4 legends here. Let me explain what they are. So there are 14 states in US which use ASHTO M332, which is the MSCR based code, right? Which are color coded with a dark gray color. So you can see here, right? Roughly about there are 50 states. Among the 50 states that are available, around 14 states are only using the MSCR based specification as on date, even in US, right? Then about 15 states are using ASHTO M332 for PMB only. So when you have a polymer modified bitumen, you use 332. When you have an unmodified bitumen, you can use any of the older codes, the 320 or 323 version. Right, so 15 states try to use ASHTO M332 only for PMB, whereas these 14 states use it for any type of bitumen. Then we have 3 states which use ASHTO M320, which is an older code, with MSCR test as a plus test, which is as a PG plus test. So that is like some 3 states here. Okay. And then 18 states are using ASHTO M320, which is the original PG specification, without any grade bumping or without any MSCR inclusion, and they are using some other PG plus test. Okay, so the entire country is actually divided on the use of tests to capture the performance of polymer modified bitumen. So though some states use MSCR, it's not completely implemented even in US. Right. Now, with this background, let us start talking about some of the issues in implementing IS 15462-2019 for India. So I have highlighted some 5 issues here. One is the temperature at which viscosity is measured. The second one is regarding the intermediate pavement temperature specified for your fatigue cracking. Third one is regarding the limits for high temperature PG. The fourth one is regarding the calculation of pavement temperature. Then the last one is the correlation between MSCR and Rutwheel test. So let's now start talking about the temperature at which viscosity has to be measured for polymer modified bitumen. So you had seen that in 15462-2019, it is specified to be measured at 150 degrees Celsius, right? But through a lot of studies, we have observed that at 150 degrees Celsius, bitumen exhibits a non-Newtonian response. Basically, the viscosity that you measure is going to depend on the shear rate, basically the speed at which you rotate the spindle, right? So in that case, when it exhibits a non-Newtonian response, you also have to specify at what shear rate you have to measure the viscosity to have a comparison between different values, right? So these are the results for PMBE. This is at 140, 150, 163. So we could see that maybe at 163, you can say it is close to a Newtonian, but otherwise at 140 and 150, it is almost non-Newtonian, right? Similarly, you can see the results for PMBP. Maybe we could say PMBP kind of exhibits a Newtonian response at 150 degrees. This was based on one particular study for a given type of modifier. To get more clarity regarding the nature of response at these temperatures, 5 or 6 samples were tested at different temperatures. So these are all commercially available modified bitumen, and they could be elastomer based or plastomer based, but only either of these two. Right, so 6 samples were collected and they were tested at different temperatures. So you could see the results. This is at 135 degrees Celsius, except for sample 4 and maybe I could say sample 2. All of them are exhibiting a non-Newtonian response. We have also shown the error bars just to ensure that the variability is highlighted. Similarly, if you look at 165 degrees Celsius, you could also see only maybe 50% of the binders are exhibiting a Newtonian response. So that is the reason why South Africa has used a higher temperature for measurement of viscosity, 165 degrees. And even in the case of rubber modified bitumen, they had gone up to 190 degrees. In IS 15462, viscosity is specified to be measured at 150 degrees Celsius, and the ASTM 4402 code is specified as the guideline. But 4402 does not give you any particular shear rate. It only gives you the procedure how to measure the viscosity. If suppose your material is non-Newtonian at 150 degrees Celsius, at what shear rate basically we should be measuring the viscosity, right? So that is something which has to be looked into when you are trying to measure the viscosity at 150 degrees Celsius for this particular material. The next aspect is the calculation of intermediate pavement temperature. You know that we are calculating the G star times sine delta value to basically capture the energy dissipation in the material, right? So the energy dissipation corresponds with the fatigue cracking. Fatigue cracking occurs when you repeatedly load the material at a specific or in a specific temperature range. Now let's look at how is this intermediate temperature calculated, right? So this is kind of the algorithm that is used in the PG specification. This intermediate PG grade is nothing but PG high temperature plus PG low temperature along with the sign convention divided by 2 plus 4. Right, so let's say I take a PG 46. This is the high temperature. This is the low temperature minus 34. So I do a 46 minus 34. Right, I get 12. I divided by 2. I get 6 plus 4. I add 10. So that is my intermediate temperature. That is the temperature at which I should check for G star times sine delta. Okay, similarly, you can check with this, right? 46 minus 40, I have 6. 6 divided by 2, 3 plus 4, 7. So like that, you can check for any temperature. This is how it is calculated. Now let me ask you this question. At this intermediate temperature, we are checking for the energy dissipation, right? Energy dissipation occurs only when the temperatures are significantly lower, when the response of the material is more solid-like. Right? So this is how the intermediate temperature is calculated in the PG framework. If we try to apply the same logic for Indian conditions, this is what we will get. So we have chosen some 5 locations here just to illustrate. Trichy, Hyderabad, Bhopal, Jodhpur and Lucknow. So this is a 7-day average maximum air temperature, 7-day average maximum pavement temperature, 1-day minimum air temperature. You can see in US it easily goes sub-zero, but in India, it is not sub-zero. In some locations, you can see it's as high as 22 degrees Celsius. Now, if I apply the same rule, right, PG high temperature plus PG low temperature divided by 2 plus 4, then I'm going to get an intermediate temperature of 46.5 degrees. Basically, we are estimating the susceptibility towards fatigue cracking using this G star times sine delta parameter. So that happens when the material is stiff, like more a viscoelastic solid-like response, right? But at 46 degrees, the material moves, it's almost in the transition region. So, depending on the conditions, it might exhibit a solid-like or a fluid-like response. But definitely, we are not going to capture the fatigue cracking response at this particular temperature. You can see for any location, it's above 40, right? So what are the issues with regard to the use of this particular temperature? The first one is fatigue cracking is, as I mentioned, is considered as a critical distress at the intermediate temperature. So at temperatures of about 40 degrees, bitumen is in the viscoelastic transition regime. In one of my previous lectures, I have mentioned what is this viscoelastic solid fluid transition and how we have tried to capture it. Right, at 40 degrees Celsius, it's more or less in the transition regime. So depending on the traffic conditions, climatic conditions, it might sometimes rutting might be a prominent one, or sometimes fatigue cracking might be prominent. So the response will keep varying. So to estimate the fatigue cracking susceptibility, we basically have to test the material at a relatively lower temperature, right? Maybe at 20 or 25 degrees Celsius, at a temperature at which basically cracking is expected to happen, right? So should we test the material at these temperatures of 31 to 40 degrees, or can we go to lower temperatures? Basically, maybe we can use the 1 day minimum. Basically, we can use the 1 day minimum air temperature or a constant temperature and then test the material, right? That is the second question that we have to look into. The third one is regarding the limits for PG high temperature, right? Let me give you a scenario, right? I am purchasing a binder which is graded as PG 70 -10. So as per the PG specification, this binder will have a G star by sine delta value of minimum of 1 kilopascal at 70 degrees, right? That is what is required to grade this binder as PG 70 -10. Now, let's say I procure this binder, I test it in my laboratory, right? I get the PG pass-fail temperature in unaged condition. Let's say, I'm just giving you a hypothetical case. Let's say it is 87 degrees Celsius. Similarly, the PG pass-fail temperature in short-term aged condition is 85 degrees. So in unaged, we have a pass-fail temperature, which is at 87 degrees Celsius, it's exactly 1 kilopascal. And similarly, at 85 degrees, it's about 2.2 kilopascal in unaged condition. Sorry, short-term aged condition, right? Now, should I call this binder as a PG 82 -10 binder or a PG 70 -10 binder? As per the specification, it is required if it has a minimum of 1 kilopascal at 70. So if you look at these values, maybe it is having somewhere around 2 or 3 kilopascal at 70 degrees. Anyway, it is meeting the requirement because the minimum value is satisfied, right? So it could be graded as a 70 -10 also, or it could be graded as an 82 -10 also. This issue occurs because we do not have any bounds for the specification parameter, and it is mentioned only as a minimum value specification. So to take into account of these kind of issues, the Caltrans Department of Transportation has come up with their own specification requirement, which is based on the PG framework, but modified to suit their requirements. So therein what they do is they give bounds for the G star by sine delta value. So they say, if you test at the at-grade temperature, say for example, for a PG 58 -22 binder, if you test at the at-grade temperature of 58 degrees Celsius, it should be within 1 to 2 kilopascal, right? So they give a bound. Now, you can, this issue, like what I mentioned here, grading as a 82 -10 as a 70 -10 issue will not happen if bounds are provided for the G star by sine delta value, right? So this is one common issue which is encountered these days because of the minimum value which is specified for the G star by sine delta value. Okay, another aspect which is related to the MSCR test, this is in concurrence with what we have been discussing before. The issue here is, at what temperature should the MSCR test be conducted? IS 15462-2019 says the MSCR test has to be carried out at the at-grade temperature. So if I have a 70 -10, I do the MSCR test at 70. If I have an 82 -10, I do the MSCR test at 82, right? Now let us take a binder which is PG 82 -10. Let's say you give me a binder, I do not know what is the grade of the binder. I go and test the binder in my lab. Then I find out that it is graded as 82 -10. Then when I give you this result, you tell me that no, it is actually a PG 70 -10 grade of binder, right? Now, should the MSCR parameters be satisfied at 82 or at 70 degrees? Okay, should I carry out the MSCR test and look for the compliance of the JNR and JNR difference for a test at 70 degrees or at 82 degrees? That is the first question. Okay, it is when you grade and when you give it to me as a PG 70 minus 10, then I should test it at 70 degrees. But you give me a binder, you don't tell me the grade. I determine the grade of the binder. Then in that case, I will be testing at 82 because according to me, the grade of the binder is 82 minus 10. Okay, but because of this minimum value specification, I can also say it at 76 minus 10 or 70 minus 10 or 64 minus 10. In fact, I can associate any grade lower than 82 minus 10. Okay, so in this scenario, at what temperature should I carry out the MSCR test? That is the first question. The second question, so accordingly, if I grade a binder, let us say I have a PG 82 minus 10 grade of binder. Okay, let's say you gave me a binder graded as 70 minus 10, but I have tested it in my lab and identified it to be 82 minus 10. Now, should I test for the parameters at the at-grade temperature, or should I test for the parameters at the temperature range in which I am going to implement in field? Let's say my location has a climatic condition which requires a PG 70 minus 10 grade of binder. Okay, then I have a 82 minus 10 grade. So again, this issue will be solved when we have bounds for the PG specification. Right, so when we have bounds for the PG specification, every binder will be graded. Every binder will be graded in a specified grade, and this kind of using the minimum value will not occur. So in that scenario, we will not have these kind of an issues with regard to the test temperature for the MSCR test. The next aspect that we would like to discuss is the correlation of MSCR test to the rutting performance. Basically, this multiple stress creep and recovery like kind of loads the material, unloads it. So for certain number of cycles. So we are basically capturing the recoverable and irrecoverable deformation of the material, right? So this is expected to correlate with the rutting performance. Let's say I am interested in characterizing the rutting performance of the mixture and see whether it correlates well with the values given from the MSCR test. Then the question now is, at what temperature should I carry out the rut wheel testing? So this is the results for a rut wheel test at 50 degrees Celsius for 4 kind of binders, a VG30, a PMBE, PMBP, and CRMB. Again, this is from one particular study. So you can see here that the rut depth is higher. It's about 30,000 passes. This is from a dry rut wheel testing. You can see this is at 50 degrees Celsius. This is VG30. This is PMBE, PMBP, and CRMB are here. Now I can show you the rut wheel test result at 60 degrees Celsius. You can see the ranking is completely different, at least for PMBP and CRMB. VG30 and elastomer are, at least the ranking is the same, but PMBP and CRMB are different. So if I want to correlate the performance, again, the performance varies with temperature. So at which temperature should I try to establish such kind of a correlation? Right, that is the first aspect. The next aspect is the relation between the MSCR and PG value. So for the same 4 binders which I have shown before, this is the PG pass fail temperature, which is the temperature at which G star by sine delta is exactly or minimum of 1 kilopascal and 2.2 in unaged and short-term aged condition. So you can see here, let's just take unaged for the moment. If I rank the binders based on their G star by sine delta value, VG30 is the least stiffest, followed by PMBP, followed by PMBE, and then CRMB. So basically, I would expect that my VG30 will have more deformation, then then followed by PMBP, then PMBE, and CRMB would give me the least deformation. Okay, so this is the PG temperature. Let's look at the JNR value. It is again calculated at 2 different temperatures. Let's just pick one set. So if I look at the JNR value here, you can see CRMB is having the least JNR, which is fine. Then it is followed by PMBE, PMBP, and then VG30. So it's kind of corresponding to the order that we have seen here. Now, if you look at the rut wheel testing results here, you can see that PMBE has given us the least rut depth, right? So MSCR test is effective, but we have to further probe this test, make a lot of correlations, do a lot of rut depth related studies, and then try to identify which parameter, maybe at what temperature, at what stress level, has a better correlation to the rutting performance of the mixtures. Right. This is the next issue that we wanted to focus. The last issue is related to the pavement temperature prediction. Right. For a PG, the grade, whatever we have, PG 64 minus 10 or 70 minus 10, whatever be the grade, that is determined from 7-day average maximum and 1-day minimum pavement temperatures, right? Basically, the SHRP equation is used to estimate the pavement temperatures. So this is the equation given here, which is also mentioned in their IRC code. This equation is based on temperature data collected for locations in the US, right? It is developed and validated for the climatic conditions in US. The climatic conditions in India are totally different, and it is not necessary that the correlations have to be valid. So to check whether these correlations are valid, what we had done is we had tried to develop a pavement temperature model for India. As of now, not much of published data, or I could say scarcely any data is available with regard to the pavement temperatures for India. So to develop this model, what we had done is we had chosen locations in US which had similar climatic conditions, or which in fact I could say which had similar latitude as that of India. Right, so these are the regions. So we identified locations in this region and then extracted the air temperature and the corresponding pavement temperature from these locations in this region. Okay, so this information was collected from a long-term pavement performance study, which is under implementation in US, the LTPP database. So the air temperature and pavement temperature data was collected, and then a regression model was used. Again, there are many parameters which would influence this correlation. If you look at the current MEPDG, which is implementing the EICM model, which is Enhanced Integrated Climatic Model, they have at least a set of 6 parameters: air temperature, humidity, wind speed, sunshine, rainfall, and some other parameter. They have a total of 6 parameters, which they think is influencing this air temperature to pavement temperature correlation. But the predominant among them are the air temperature and the latitude, right? Which determines, the 6th one was radiation. So this latitude determines the radiation that is experienced at a particular locality. So that is why for this study, we just chose only 2 parameters, which is air temperature and latitude. And then this was the regression model that was used to establish the relation between air temperature and pavement temperature. And based on this temperature, contours were developed. Again, you should remember that none of the data, except for the air temperature, none of the data that is used for this particular case is from India. The locations which were used for development of the model is from US. This model was validated with one particular set of data. It was collected from Highway Research Station, which was like as early as 1969. For one particular day, for each hour, the air temperature and the corresponding pavement temperature was available. So only that particular data was used to validate the model. And we had seen that compared to any other models available before, this regression model was able to better predict the air temperature, pavement temperature data available for India. Right. So based on this model, we used air temperatures for about 40 locations in India, calculated the pavement temperatures, and developed a pavement temperature contour. Right. We classified them into different temperature ranges. And this is the maximum pavement temperature contour, and this is the minimum pavement temperature contour. But I should mention here that this is quite approximate because we have not developed the model for Indian conditions nor validated it. Basically, we should be collecting a lot of data in India, collect pavement temperatures at different locations, the corresponding air temperature, and then try to develop a correlation. So what is the limitation in using the existing information? Like I said, the database for development of regression model was used from US. The validation was done only by by using one set of data collected by Highway Research Station in Chennai. And like I said, the choice of parameters in the regression model, we used only air temperature and latitude, but other parameters could also have significant effect. We don't know. For the Indian conditions, we have to check the sensitivity of different parameters, right? So to summarize, we have to collect more data from modified binders manufactured in India and check how these binders are complying to the existing specification. Similarly, we also have to collect a lot of data with regard to pavement temperature to develop an in-house model to predict pavement temperature from air temperature. The intermediate pavement temperature requirements also have to be addressed. Whatever is given for US climatic conditions are more towards the higher range, wherein the fatigue cracking may not be that prominent, right? So we should identify different set of temperatures at which this G star times sine delta parameter will be checked. Similarly, viscosity at 150 degrees corresponds to mostly non-Newtonian regime for many types of modified bitumen. So this also has to be checked. And then better parameters have to be identified to correlate the rutting susceptibility of the binders to that of the mixtures to that what is experienced in field. Thank you.